All right, as promised, we're going to work through some problems on quiz 11I. So this is an example of the quiz that we're going to be going through on Tuesday in class. All right, so it's really just one big problem with multiple parts. I'm not entirely sure how many of these I'll be able to get through in this one video because it could get kind of long. So we're going to look at the first part. So we've got a diprotic base B that reacts with water as follows. It gives us our KB1, our PKB1, our KB2, and our PKB2. Okay, and then it asks us to calculate the pH of a solution containing 0.087 molar of B. All right, so we're going to need to remember what the formula is for KB here. So I'm going to write this KB1 is going to be equal to the concentration of HB plus times the concentration of OH negative over the concentration of B. And so what we're doing here when we're calculating and figuring out which one to set it equal to is we're trying to figure out which one has the B in it. Okay, because we're matching up species. So equation 1 with the KB1 here has B, and then that is a reactant. And then on the product side, you've got HB plus and OH minus. So remember, it is products over reactants when it comes to this. So that is where I plugged in those. Okay, so now we know that at the equilibrium, HB plus and OH negative are going to be equal. So we're going to set those as X, and that's going to be X squared over the concentration of B. All right. So we were given our concentration of B as 0.0087 molar. And so we're going to solve for X in order to get our hydroxide ion concentration, and then go from there to pH. All right, so we're going to go ahead and we've got our X right here. We're going to rearrange this equation so that we're solving for X. So X is going to equal the square root of KB1 times 0.087, which is our concentration of B. All right, and when you do that, you're going to come up with X is going to equal 0.00243. And remember, this is also equal to the concentration of our hydroxide ion. All right, so it's fairly simple to go from here to pH, because if you'll remember, the negative log of our hydroxide ion concentration is our POH. All right, so we're going to go ahead and write that in. Negative log of OH, and that is going to equal the negative log of 0.00243. And then when we equal that out, our POH is 2.614. And then we subtract this from 14 to get our pH is going to equal 11.39. Okay, so that's the answer for part A. Now, it says calculate the pH of a solution containing 0.068 molar H2B2 plus. And again, we've got to figure out which KB value we're looking at here. Okay, so for H2B2 plus, we are looking at KB2. All right. And then if you remember our relationships between KB and KA, our KB2 is going to go with our Ka1 to equal Kw, right? So that's the relationship there between that. So we have got to figure out what our Ka1 is for this reaction. All right, so if we rearrange this equation to solve for Ka1, we're going to get Ka1 is equal to Kw divided by Kb2. And when we plug our numbers in, Kb2 is 4.5 times 10 to the negative 9. We're going to get our Ka1 as being equal to 2.22 times 10 to the negative 6th. Now, we've got our Ka1 value. We need to find our hydrogen ion value, okay? Our H plus value. So we're going to put in our Ka equation here. Ka1 is going to be equal to A minus times H plus over HA. Now, if we sub in our actual letters for our reaction here, this is going to be H plus times HB plus, because remember this is diprotic, and then that is going to be over the concentration of H2B plus 2. Now we've got our concentration for H2B plus 2. So what we're solving for is these two concentrations. And so that's going to equal x squared over, we're going to put in our numbers here. And then we're going to solve for x. So x is going to be equal to the square root of Ka1 times 0.068, and that's going to give us x is equal to 3.887 times 10 to the negative 4. That is our hydrogen ion concentration, so we're going to plug that into the pH formula. So pH is equal to the negative log of our H plus and that's going to give us, our pH is going to be equal to 3.41. All right. So I'm going to stop this video here because it's already getting kind of long, and then we will do the next 3 sections in the next one. All right, let's look at section C. Okay, section C asks us to calculate the pH of a solution containing 0.100 molar Hb plus. Now, with this one, because Hb plus is what is considered an intermediate species, we have to use a little bit different equation to get this. Okay, and what he is wanting us to use, the equation to get pH, is equal to 1/2 pKa1 plus pKa2. And the reason behind this is that as the species dissociate, for the first step, you have not a huge value because weak acids don't dissociate fully. But then that step gets even, that value gets even smaller for the second one. So your pH is going to be midway between your two pKa values, regardless of the concentration. That is the theory behind the intermediate equation there for this. Because this is, it can either take on a proton or it can give up a proton. So you're considered intermediate. You can be an acid or a base at this point. So this is the equation that he's wanting us to use. Now, I looked at his key, and he has got some weird math magic going on in calculating the pKa1 and pKa2. And I am just going to calculate it otherwise to where it makes more sense to me, because I figure if it makes sense to me, it's probably going to make more sense to you guys. So we already know, we have found out in part B what our Ka value is, right? We did that right here. And we know that pKa is the negative log of our Ka value. So if we do the negative log of 2.22 times 10 to the negative 6th, that is going to give us, hold on, 5.65. All right. And then for pKa2, what we're going to do is we're going to take our Kw and we're going to divide that by our Kb2 to give us our Ka1. And then when we sub those numbers in, $6.8. All right, so this one was pKa1. All right, so we're trying to find pKa2, so this should be Kb1 that we're putting in here, which if you look, I can get it up here. Ka1 is the 6.8 times 10 to the negative 5th. All right, and we are going to solve that. And that is going to give us a Ka2 value of 1.47 times 10 to the negative 10. And then we take the negative log of that to get our Ka2 value. Sorry, our pKa2 value, okay? And that is going to equal 9.83. All right. So now we're going to plug all of this into this equation. So our pH is going to equal 1/2 of our pKa1 plus our pKa2. And then that is going to give us our pH is going to equal 7.74. Let's move on to section D. So section D is using the Henderson-Hasselbalch equation along with our pKa2 value in order to find pH. And again, we can figure out which value we're going to be using based on the species that are involved. So our reaction that we're looking at here, I know I'm turning this weird. I'm not sure if it's going to be easy for you guys to see. B, and then we're going to add water to that. So we're going to go through hydrolysis. And that's going to give us this one, okay? So our Kb value, this was Kb1. And our Kb value was 6.8 times 10 to the negative 5. Our, we just found our pKa value for this one. And remember, because we've got Kb1, we're looking at Ka2, so pKa2 is the one that we're looking for here. And that one was 9.83. So pKa2 is equal to 9.83. All right, and then we're going to do a plus the log of our concentration. So we're just going to do this. pH is equal to our pKa plus the log. And remember, we are doing our B, okay, because that is our reactant, over our products. Okay, so it's 0.094 over 0.065. Plug that into the calculator, and that's going to give us a pH of 9.99 on this one. And then last problem for this one, we've got to find the pH of a solution containing 0.12 molar of HB plus and 0.14 molar of H2B2 plus. All right, now let's go back up and look at our reactions. So for HB plus is an intermediate. Okay, so it is in both of them, but we need to find it in with H2B2 plus, which is our KB2 reaction there. All right, so KB2 times Ka1, that is our relationship. Okay, so we've got to use our pKa1 in our Henderson-Hasselbalch equation for this one. So our pH is going to be pKa1 plus the log. And remember, it's reactants over product. So our reactant is HB plus over our product. And then we're going to sub in our numbers. Nope. How about wrote the wrong one down? Okay, so pKa1 was 5.65 plus the log of 0.12 over 0.14. We run those numbers, and that's going to give us a pH of 5.58 on that. So this is a lot of the same equations that we used last time, just made a little bit more complicated by the relationship between the Ka and Kb of the polyprotic acids and bases, diprotic acids and bases. It gets more complicated the more hydrogens that you throw in there with it. So if you guys have any questions, let me know. You can text me, email me, drop me in the comments, whatever you want to do. If this does not make any sense, please let me know that it doesn't make any sense, and I'll try to make it a little clearer. Talk to you guys later.